Hello friends, today we are going to discuss questions from 2017 and there are total of 5 questions of 2017 and they are from mains as well as advanced. So first question, it was asked in the year 2017 mains and it states that a diverging lens with magnitude of focal length 25 cm is placed at a distance of 15 cm from a converging lens of magnitude of focal length 20 cm. A beam of parallel light falls on the diverging lens. The final image formed is. So we are given that we have a diverging lens as well as converging lens. So one will be concave and another one will be the, you can say, convex. And it is given that a parallel beam of light falls on the diverging lens. Okay, so it is quite obvious that you can say, okay, let's first of all draw the figure, then we can discuss what is going to happen. So we are given that we have a diverging lens and for this diverging lens will be our concave and its focal length it will be our minus of 25 centimeters, and then we have converging lens so converging will be our convex and its focal length will be equal to plus 20, and the distance between the lenses is given as 15 centimeter. Distance between the lenses it is given as 15 centimeter, and it is said that the beam of light is parallel you can say on the diverging lens. So we are given that beam of light is parallel to the not to the but incident on the diverging lens, is parallel incident on diverging lens. So we can draw an approximate figure for that, and this is our diverging lens, and then there will be a converging lens, and the distance between the two is given as 15 centimeter, and the ray of light, their axis should be common, not mentioned in the question, but it has to be same, and the ray of light is parallel, that is falling on the diverging lens. So it is coming like this. So it will diverge. Let us suppose something like this, and it will be falling here, and same will be here. So we can just make it a solid one, and they will be converging on the back side and forming an image. And we are given its focal length is 25 and focal length of the lens is given as 20 centimeter. Okay. So we can say that especially for the diverging lens, it is given that it has a incoming as a parallel rays, and if we make them converge, and they will be converging like some here at a focus. Okay. So this will be a focus of our diverging lens. So let us call this as f1. Because for diverging lens, you can say that but they converge as if they converge at the focus. Let me write straightforward. They converge at focus, or we can say they appears to converge at focus. That would be much better. They appears to converge at the focus. So therefore, the image that will be formed, let us call that I1. That image will be imaginary. Okay, sorry, not imaginary but virtual. So we can say that the virtual image appears at focus. That is, we can say that our V will be equal to minus of 25 centimeters. And this image will be acting as object for the our converging lens. You can say this image will act as object for converging lens. Therefore, we can say the distance of the image I1, that will be you can say object for the converging lens. So this distance will be about 25. So the total distance will be our 25 plus 15. Okay. So that will be our 40 centimeters. So we can write that our V will be equal to U, and that will be equal to minus of 25 plus 15, giving us a minus 40 centimeters. And now we can use the lens formula for the converging lens. Lens formula, we can write 1 upon V minus 1 upon U is equal to 1 upon F. We substitute the values and we get from here, let me write this as V1. Okay, so this is V. So we get 1 upon V is equal to 1 upon F is plus 20, and 1 upon U will be equal to a minus of 40 rather, and then it will be coming as minus of 40. So this gives us that our V is equal to 40 centimeters. this is the position of our, you can say, the image, and this V is positive, so obviously the final image will be formed at a distance of 40 towards the right. So we can draw an approximate figure for that also. So it will be converging somewhere here, and this will be a final image, that is I, at a distance of 40 from our converging lens. And the options that are given, that it is real at a distance of 40 from the convergent lens. Okay, so option number D is the correct option. So you can say option D is correct. D is correct. We come to the next question. It was asked in the year 2017 mains, and it states that in Young's double slit experiment, slits are separated by 0.5 millimeter and the screen is placed 1 centimeter away. A beam of light consisting of two wavelengths, 650 nanometer and 520 nanometer, is used to obtain interference fringes on the screen. The least distance from the common central maxima to the point where the bright fringes due to both wavelength coincide is. So we have to find out the position where bright fringes due to both wavelengths. Okay, one wavelength is 650, another wavelength is 520. They should be coinciding, and we have to find out with respect to the common central maxima. Okay. So we can just put the data which is given to us, and first of all we are given the split distance between the splits, that is of small d. So we can write this as small d is equal to 0.5 millimeter, and that will be coming as 5 into 10 to the power minus 4 meters. And then we are given as capital D, that the distance to the screen, which is our 150 centimeters, and that will be our 1.5 meters. And the last thing that is given are two wavelengths. Let us call them lambda 1, that is our 650 nanometer. It means 650 into 10 to the power minus 9 meters. Second wavelength is lambda 2, which is our 520 into 10 to the power minus 9 meters. And we have to find out the least distance from the central maxima when the bright fringes of both, you can say, are going to coincide. Okay. So this, you can say, we can sort it out by, so we have two wavelengths. So we can say, we have to find out rather the LCM of fringe positions we have to find out the LCM of fringe positions, fringe positions, okay, for two wavelengths, Okay. And so we already know the fringe position formula, and that formula is given as, we have fringe position that is given as y, and will be equal to n lambda multiplied by capital D divided by small d. Okay, and this is for nth bright fringe. wavelength bright fringe. And for, you can say, for the wavelengths, if they have two coinciding, then for different wavelength we can write this as, we have two wavelengths, so we can just modify the formula. We can write for first wavelength y1 will be equal to n lambda 1 d divided by small d, and for the second wavelength we can write this as n2 lambda 2 d and small d. And for condition for coinciding, condition for coinciding y1 should be equal to y2. Therefore, we substitute, we get this as n1 lambda 1 d upon small d is equal to n2 lambda 2 capital D and small d. Here this d and d cancels out. So from here we get that our n1 lambda 1 is equal to n2 lambda 2. And we can use, you can say, the LCM to find out the LCM of the bandwidth, because we require them to be a common multiple. So let's find out the LCM. So you can say LCM of 650 and 520, and that will be coming as 2600 nanometer. So we can find out the distance from central maxima distance from central maxima. We can write that our y will be equal to LCM of the wavelength, which we just found out, capital D divided by small d, and this comes as 2600 into 10 to the power minus 9 multiplied by 1.5. Small d is given as 5 into 10 to the power minus 4, and this comes as 7.8 millimeter. Okay. So for the consider, you can say the condition for coincidence is given as 7.8 millimeter, and the option number A is the correct one. Option A is correct. We come to the next question. Okay, it was asked in the year 2017 advance, and it states that for an isosceles prism of angle A and refractive index mu, it is found that the angle of minimum deviation delta m is equal to A. Which of the following options is or are correct? So we are given that the angle of prism is A, and that is equal to the minimum deviation. Okay. So we can just draw in a for approximate figure for that. And suppose this is normal, we have angle of incidence, that is, let us suppose, given as I1, and this will be our refraction R1, and on the other side this will be our angle of emergence, and we are going to have this will be our R2, and this is our angle of prism A. So let us call this as B and this is C, and let us call these points as P and this point as Q. And for minimum deviation, the condition which is given to us is that our delta m is equal to A. Okay. You can see that condition for minimum deviation as per the standard formula, the angle of incidence, that is I1, should be equal to angle of emergence, and our R1 should be equal to R2, and that should be equal to A by 2. And we can assume that both R1 and R2 are equal to a common, that is our R. And also the standard formula for the minimum deviation, that is of delta m, that is given as 2I1 minus A. Okay, it is basically, let me write this formula is basically our I1 plus E minus A, and I1 and E are equal, so we can write this as 2I1 minus of A, and we are given that our delta m is equal to A. Okay. Therefore, we substitute it, we get A is equal to twice I1 minus of A, which gives us that twice I1 is equal to twice of A, and this 2 goes with 2, and we are left with that our I1 is equal to A. Okay, and obviously that will be also equal to angle of emergence. All these three will be equal. Okay. And we know that R1 is equal to R2 is equal to A by 2. So from here we can write that our R1 is equal to R2 is equal to, suppose, R, and is equal to A by 2, and now A is equal to I1. Therefore we can write that our R1 is equal to I1 by 2. Okay. So we found out the angle of refraction in terms of angle of incidence. Okay. So therefore option number B is the correct one. Option B is correct. And we can also use the Snell's law at point P. Snell's law at P, and we get this as, okay, so we are given refractive index of, okay, the refractive index of glass is mu, it is given to us. So therefore, we can write the Snell law gives us that a mu is equal to, we have this as sine of I1 divided by sine of R1, and I1 is equal to A and R1 is equal to A by 2. So we can put it here, and we get sine of A and divided by sine of A by 2. And now we can use some trigonometry identity which gives us that mu. We get this as 2 sine A by 2 cos A by 2, and then in the denominator we already have sine of A by 2. So therefore sine A by 2 and sine A by 2 cancels out, and this gives us 2 cos A by 2. And we can also use and we need to find out that it states that for angle of incidence I is equal to A, the ray inside the prism is parallel to the base of the prism. Okay, we can just prove that also. And another option is that for this prism, the refractive index mu and angle of the prism A is related as A is equal to half cos inverse and mu by 2. Okay, so let me write it here. So my mu is equal to 2 cos A by 2. I think, yeah, I need to find out A. Okay, so from here I can find out my A, and this gives us that my A by 2 will be equal to cos inverse mu by 2, and A will be equal to 2 cos inverse mu by 2. Okay. So I think this was asked. No. So this is, so option number D is incorrect, because here it is asked that it should be so angle of the prism, that is of A, is coming as equal to A2 cos inverse mu by 2. Okay. So option number D is incorrect. Okay. And okay, so let's draw the other figures, second figure, and for that we can just so this is our normal incident ray, and this is our refracted ray, this is our point P, and once again we have this as I1, this will be R1, and this will be R2, and our refracted ray just grazes our prism. So this is our A, B and C, and this is our angle of the prism. So this is a point P and this is our point Q. So if we use Snell's law at point Q, Snell's law at Q, we can write that our mu is equal to, this angle will be 90. So we have this as sine of 90 divided by sine of R2. So from here we can find out our R2 will be equal to sine inverse 1 upon mu. But we already know that for R1 plus R2 is equal to A. So from here we can say our R1 is equal to A minus R2. We substitute our R2, we get our R1 is equal to A minus sine inverse 1 upon mu. Okay. And similarly, we can use the Snell's law at P. So we can say Snell's law at P, which gives us that the mu is equal to sine of I1 and divided by sine of R1. And R1 we just found out, we substitute the value, and from here we get that our sine of I1 is equal to, we can write this as mu, and this is sine of, we substitute value of R1, which is A minus sine inverse 1 upon mu, and this gives us that our I is equal to sine inverse mu sine of A minus sine inverse 1 upon mu. So this is our angle of incidence, and so option number C is the correct one, because here it says that emergent ray at the second will be tangential. Okay, so this is our tangential ray, and for tangential ray we can say the angle of incident is given by this. So we can say option number C is correct. C it is. Yeah, option C is correct. Okay, and finally it says that for the angle of incident I1 is equal to A, the ray inside the prism is parallel to the base of the prism. And for minimum deviation, we already know that the ray which should be inside the prism has to be parallel to the base. You can say for minimum deviation, our PQ should be parallel to BC. So therefore option A is correct. Option A is correct. So we have three options A, B, C are correct. Option D is incorrect, because here we get 2, not 1 by 2. We come to the next question. It was asked in the 2017 advance, and it states that two coherent monochromatic point sources S1 and S2 of wavelength 600 nanometer are placed symmetrically on either side of the center of the circle as shown. The sources are separated by a distance d, that is, it should be 1.8, not 18, 1.8 millimeter, or it is 18 millimeter. 18 millimeter. This arrangement produces interference fringes visible as alternate bright and dark spots on the circumference of the circle. The angular separation between two consecutive bright spots is delta theta. Which of the following options is or are correct? So here we are given this figure and two sources, coherent S1 and S2, and they are going to form alternately bright and dark spots. And we have to find out, there are two, you can say, points marked. One is P2, another one is P1. So all these options are with respect to P1 and P2. Okay, whether they will be dark spot or bright spot, and the fringes produced between P1 and P2. Okay. So we are given wavelength, that is our lambda, which is our 6 into 10 raised to power minus 7 meters, and separated by small d, which is our 1.8 into 10 raised to power minus 2 meters, and the position is symmetric about the, you can say, about the center of the circle. So position is symmetric about center of circle. Center of circle. Okay, and the interference fringes are on the circumference of the circle. Interference fringes are on circumference of the circle. Okay. And we are given 2 points, one is P1 and P2, and from the figure itself it is clear that they are in first quadrant and the angle theta is going to vary from 0 and to 90 degree. Okay. So this is the position of P1 and P2. So you can say that P1 and P2 first quadrant and theta, it varies from 0 to 90 degree. Okay. Yeah. So let us find out what will be the interference condition that is at an angle of theta from the center axis. Interference condition on the circumference of the circle, and the path difference, we can write that if for the path difference of because if r is the radius of the circle, then the both sources will be equidistant from the center. So let us say that if r is the radius, then S1 and S2 are equidistant from the center. Therefore, the path difference at an angle of theta, the path difference at angle of theta, we can write that delta of x is equal to d sine of theta. And for, we can say, the interference fringes are going to take place if this path difference is equal to integer multiple of the wavelength. You can say the interference fringes occur when the path difference equals the integral multiple of wavelength. Path difference equals integral multiple of wavelength. So we can write that our delta of x will be n times lambda, and from here we can write our d sine of theta will be equal to n times lambda. This gives us that sine of theta will be equal to n lambda by d. And the angular fringe position, if that is theta n, so you can write that angular fringe position theta n will be equal to sine inverse of n lambda divided by d. And the angular separation decreases from P1 to P2. You can say the angular separation decreases from P1 to P2, and we can also say that n increases the change in angle, that is our delta theta, the change in angle, that is our delta theta, will be equal to theta n plus 1 minus theta of n, and decreases because of sine inverse function, because sine inverse of x, it is we can say sine inverse of x grows slower as x approaches 1. So from here we can draw a conclusion that the angular separation becomes smaller as we move from P1 to P2. So this option is our correct one. So option number A is correct. Option A is correct. We come to the next part, that the dark spot that will go with respect to P2. Will be formed at P2, and so we can say that the maximum possible order between sine of theta, as it varies from, will be equal to when sine of theta is equal to 1, because at that particular position our theta will be equal to 1. So we can say that maximum possible fringe order, if represented as n max, is when our sine of theta is equal to 1, or we can say our theta is equal to 90 degree. So we can just find out our n max. We already know the relationship between n and sine of theta. So we can say n max will be equal to our d upon lambda, and d we already know is 1.8 into 10 to the power minus 2 and divided by 6 into 10 to the power minus 7, and this comes close to 3 into 10 to the power 4. So this is our basically a bright fringe, not a dark one. So this is we can say at sine of theta is equal to 1, or we can say theta is equal to 90, we are going to get a bright fringe. Therefore, the option is incorrect. Okay. So we have the P2 is incorrect. Option B is incorrect. And we can find out the total number of fringes between P1 and P2. Total number of fringes between P1 and P2. And the fringe, let us suppose that is of n, will be equal to d sine of theta divided by lambda, and we can say at theta is equal to 90, our value of n, we just calculated it, it is same repetition, that is 1.8 into 10 to the power minus 2 divided by 6 into 10 to the power minus 7, and this gives us 3 into 10 to the power 4. And the total circle is going to have 2 into 3000. You can say that total number of fringes in entire circle is equal to 2 into 3 into 10 to the power 4, and this comes as 6 into 10 to the power 4. And for a quarter circle, that is for first quadrant, we can say that that will be equal to 1/4 of the total, that is 10 to the power minus 10 to the power 4, and this comes close to as 7500, which is not our 3000. So this option is also our incorrect. So option C is also incorrect. Option C is incorrect. And last one, which says that P2 is maxima. So for our P2, that is our theta is equal to 90 degree. So which means sine of 90 is equal to 1, and we can say our n max will be equal to d upon lambda, which we just found out is 3 into 10 to the power 4. So option number D is also correct. Option D is correct. So we have two options. A and D are the only options which are correct. Next question. And here it is said that one second, I think I made a mistake. total number of fringes. Yeah, I think there is some calculation. 1 second. Yeah, because we just, yeah, that's my mistake, because I took the angle for 90° and then I made a mistake of, yes, so this is, sorry, so you can say that the total number of fringes between P1 and P2 is, first quadrant is close to 3000. Okay. So between P2, P1 and P2 we are having close to 3000. It is 1.8 into, 1 second, yes, this is, yeah, 1.8 into, yeah, my mistake, it is should be 1.8 into 10 to the power minus 3. This is the problem. And here also minus 3, and now it will be coming as 3000. So 3000, and here also it will be 3 and giving us this as 3000. Okay, so let me correct myself. So we get option number C is the correct one. Okay, and the order of P2 is fringe maximum. D is already correct, C is correct. Okay, and this will be also incorrect one. Okay. Yeah, so here I made a mistake of, yes, so let me correct here also. And we already know that for maximum P, our d cos of theta is equal to n lambda, and from here if you derivate it, we get this as d minus sine of theta, d theta is equal to d of n multiplied by lambda. Now we can easily find out angular fringe width. Okay, that was a mistake. I need to find out d theta by dn. If consider magnitude, that will be equal to lambda divided by d of sine theta. Okay. So it means as my theta is going to increase, this d theta by dn is going to decrease. Okay. So this option number A is also incorrect. Option A is incorrect. No, it's the correct one. Okay. Yeah, so this completes the, sorry for this mistake. We come to the next question, and here it was asked in the 2017 advance and it states that a monochromatic light is traveling in a medium of refractive index n is equal to 1.6. It enters a stack of glass layers from the bottom side at an angle theta 30 degree. The interface of the glass layers are parallel to each other. The refractive indexes of the different glass layers are monotonically decreasing as nm is equal to n minus m times delta of n, where nm is the refractive index of the mth slab and delta n is our 0.1. The ray is refracted out parallel to the interface between m minus 1 and mth slabs from the right side of the stack. What is the value of m? So this is the given figure. So ray of light is incident at an angle of theta, and finally it is coming as a parallel between the layer m and m minus 1. And we are given the relationship between, you can say, nm, that is mth layer refractive index is given as n minus m delta of n. And here it is mentioned that the refracted ray comes parallel to the interface, so it basically means that the angle of refraction at the mth slab will be equal to 90 degree. Okay. So we can just draw an approximate figure for that. We are only going to draw the incident part, that is angle of theta, and the final part which states that the ray of light will be coming parallel. So here it will be our 90 degree. Okay, and this is our mth layer. Okay, and this is our layer number 1. And we can just use the Snell's law, and Snell's law is, you can say, we can directly apply Snell's law between the initial interface and the final interface. Okay, or we can say interface between the initial medium and the mth medium for this particular question. So you can say Snell's law, which is given as n1 sine of theta 1 is equal to n2 sine of theta 2. And for this particular problem, we apply Snell's law at the interface between the initial medium and the mth medium, or we can say mth slab. Therefore, accordingly, we can modify it. So we are going to get that our n1 is equal to n, which is equal to 1.6, and the theta 1, which is equal to theta, is equal to 30 degree, and our n2 is the refractive index of nm, which is given as n minus m multiplied by delta of n, and our theta 2 will be equal to 90 degree. So we substitute these values in the Snell's law, and we get this as sine of theta is equal to n minus m delta of theta, and here will be sine of 90. Theta is our 60, so we substitute the values. We get sine of, theta is 30 and will be equal to, here we have n, and this comes as 1.6 into sine of 30, n is 1.6 minus m, delta theta is 0.1, sine 90 is 1. Now we can easily solve it for m, and we get this as 1.6 and multiply by 1.2. This goes as 1.6 minus, we are going to have this as m by 10, and we can write this as that our m by 10 is equal to 1.6 minus 1.6 divided by 2. Okay. So we get this as m by 10 is equal to, this will be coming as 16 by 2, which is our m is equal to 8. Okay. So this is the value of m which we are supposed to find out. Here the important part is only one thing, that if all the interfaces are parallel with each other, we can straightforward apply the Snell's law between the initial and final, because the intermediate one will shift from one to another, giving a final relationship between the initial as well as the final. So we apply the Snell's law directly between the initial and the final. Only condition is that they have to be, all the mediums should be parallel with each other, and in the question itself it is mentioned that the interfaces of the glass layers are parallel to each other. Okay. So we can just directly apply the formula for the Snell's law. Even if we apply the Snell's law at each intermediate point, like this and goes on, there you can say the respective refractive angles are going to balance each other or substitute each other, giving us a final relationship between the final one and the initial one. So the intermediate refractive indexes, refractive angles doesn't matter at all. So we apply directly, and that is going to give us that our value of m is equal to 8. So these were the questions that was asked in the 2017. These complete all the questions. Thank you.